So in this short video, I just want to explain a few things which we didn't touch on more detail in the lecture, and this will give me a chance to explain a little bit more what we were talking about when we were discussing the possibility to measure the total gravitating mass in an X-ray cluster in the cluster using the temperature of the hot gas which fills the volume of the cluster. And in order to understand what we're talking about, I just want to show you two pictures side by side, which is the Coma Galaxy Cluster, which is a nearby galaxy cluster that we have been observing for a long, long time and has been known also to contain lots of dark matter already from the velocity dispersion measurement. On the left, you see the optical image. The optical image is taken with Hubble Space Telescope. It's a multicolor image, so you can see here some information relating to the spectral type of the stars. And the way it's shown is that most of the yellowish galaxies belong to the galaxy cluster, and you see that they are certainly not completely relaxed. There's two indications for that. One is that the distribution of galaxy clusters is not evenly distributed around the central part of the cluster, but seems to be falling in two lumps, one to the left and one to the right. And furthermore, you see that there's two galaxies which are circled here in white on the left and on the right. And these two galaxies are giant elliptical galaxies, and these are typically the galaxies which form only in the central region of galaxy clusters. Often enough, they are located at the dynamical center of the galaxy cluster, and they are believed to be the result of multiple merging events of galaxy clusters, where in the end also galaxies start to merge and form giant ellipticals. Now, the fact that there's two of them indicates that the system is not completely relaxed, but very likely is still showing some evidence for the disturbance due to the collision or the merging event of two galaxy clusters, which form today a gravitational bound system, which we would call the Coma cluster. Now, on the right, you see now a completely different picture. It's false color, same part of the sky, and what we're looking at here is the X-ray emission. Now, most notably, the X-ray emission is quite strong in the cluster, and it's very pronounced. I mean, on the left side, you may even have a hard time picking out what's a galaxy cluster and what's just foreground of field galaxies. On the right, it becomes very clear that there is something which is sticking out strongly against the background emission. That's the emission coming from the intercluster gas, which is invisible in the optical because it's simply too hot. And furthermore, you see that the intensity, which is in this false color image depicted going from green to yellow to red, is the strongest in the central part of the galaxy cluster. And you see only a few individual galaxies which emit also bright X-rays, whereas the bulk of the galaxies do not show any prominent X-ray emission. The second thing which is notably in the Coma cluster is that you see also a second maximum in the X-ray emission, which again indicates that the system is not completely relaxed, so it's not completely virialized, and even the X-ray emission still hasn't sort of found its new shape yet. Now, the simplest way of analyzing this is to assume that there's a hydrostatic equilibrium and that the system is spherically symmetric. So then we can use the equilibrium condition shown here, so that pressure is balanced by the gravitational impulse, so phi is the gravitational potential, can be used to calculate the total mass within a radius r, and with a little bit of calculation, which is shown in some of the other notes that I distribute along with the course, you find this equation here, and it's quite obvious that the total mass is related to the product of the temperature and the radius. These are the main quantities that you could measure, and which we can use then to infer the unknown total mass. When we talk about total mass, this is the mass which is self-gravitating, which is keeping the cluster bound and which is forcing the gas to stay in that volume and not leave because of simply evaporating away. Now, the terms in the parentheses seem at first glance rather complicated, but all they're showing us is the profile of the density and of the temperature of the cluster, which we can both get a handle on by measuring the X-ray emission. And you get in the end that they both follow roughly a power law, where the slope of the density goes, the power law is such that rho goes with r to the -2, and temperature goes with r roughly constant, or maybe slightly going down with increasing radius. Even though it's a little bit more complicated than that, this is roughly telling us that the solar system behaves pretty much like an isothermal gas. Now, so the main dependence of its mass is related to product of temperature and radius. And if we assume now for simplicity that mass scales with r cubed, this is often called a self-similar model or self-similar assumption, which basically tells you that the density is constant and it just scales with r cubed. Then we can reformulate this dependence to put this in the way that we put mass is correlating to temperature to the 3½ And this is pretty much confirmed with data. So here's a plot from the review article from Boehringer and Werner from 2009, where you see the mass plotted over the temperature. Never mind the mass measure here, M500. This is a particular choice of the radius, which depends upon the density of the cluster at that distance. And on the other axis, it's the temperature of the X-ray emitting gas in units of keV. And this is roughly 1 decade of temperature and a little bit more than 1 decade of mass, so between 10 to the 14 to 10 to the 15 solar masses. The takeaway message from this plot is that this self-similar solution holds almost over the whole range. There is some deviation at the low temperature range, which may indicate that this is also where some additional effects, which we didn't consider, come into play, but the deviation is not very big. So the best fit power law is 1.7 instead of 1.5. And the uncertainty is like 0.09, so it's quite close actually to this 1.5 self-similar scaling. Now, the other thing which is notable is that the mass ranges that we infer from these X-ray measurements, and we're talking here about the total gravitating mass, is very similar to the one that we got from the measurement of the velocity dispersion, as well as from the gravitational lenses, which give us a completely consistent picture using 3 completely different assumptions, 3 different ways of measuring the mass using different assumptions, where the gravitational lens measurement is probably the least sensitive to the assumptions because we do not need to have a virialized or isothermal system, for example.